Okay, let's dive into this. We are tackling a paradox that drives JavaScript developers absolutely nuts, and it's all based on a fantastic article by Aaron Rose. You know, it's one of those head-scratchers that pretty much everyone runs into, and today we are going to crack it wide open. So it all really boils down to this one question, right? You've done everything you're supposed to do. You pushed all the heavy lifting into asynchronous tasks so the main thread stays free, but your beautiful loading spinner, it's just frozen solid. Your whole app just feels broken, even though it's chugging away in the background. So what on earth is going on?
Let's meet Timothy. He's a dev, just like us, and this is basically him, just baffled, staring at his screen. He's using promises, the modern standard way to handle async code. He's even tried some clever tricks to get that spinner animation to start before the heavy work kicks off. Logically, everything he's done should work perfectly, but it doesn't.
Well, the root of the problem, as Timothy is about to find out, is this flawed assumption that a lot of us have. We kind of think that when we make our code asynchronous, the browser just politely juggles everything, giving each little task a turn. But that is not how it works, not at all. There's a hidden hierarchy at play here.
Okay, so let's take a look at Timothy's setup. Over on the left, he fires up his spinner with a set timeout. He's thinking, 0 delay, this has to run first, right? Then, on the right, he starts crunching a huge data set with a chain of promises, thinking this'll all just happen quietly in the background. I mean, it seems like a perfectly reasonable way to do it, but it's about to run headfirst into one of JavaScript's secret rules.
To understand that secret rule, we have to talk about the JavaScript event loop. And the source for today's explainer gives us this absolutely brilliant analogy from a developer named Margaret. Think of the event loop less like a juggler and more like a nightclub bouncer.
So the bouncer's job is pretty simple. When the club's main dance floor, what we call the call stack, is empty, he goes outside to see who he should let in next. But here's the twist. He's not looking at just one line of people. He's managing two completely separate lines, and believe me, they do not have equal priority.
And this slide lays it out perfectly. These are the two lines. On the right, you've got the Macrotask queue. Think of this as general admission for all the everyday tasks. And on the left, you have the Microtask queue. This, my friends, is the exclusive VIP line.
So who gets to be in which line? Well, as you can see here, promises are total VIPs. Every single .then you write puts a task straight into that high-priority Microtask queue. But now, look at who's stuck in general admission. Set timeout, and, this is the critical part, UI rendering events. Our poor spinner animation is just stuck waiting patiently in that really long line. Now, the bouncer's rules are incredibly strict, and you have to understand this part. First, he waits for that main dance floor, the call stack, to be empty. Then, and this is the absolute key, he turns to the VIP line and lets every single person in until that line is completely, totally empty. Only after the entire VIP line has been cleared will he even glance over at the general admission line to let just one single task through. Then the whole process starts all over again.
And right there, that's it. We can now see exactly how Timothy's code created that frozen UI. His code didn't just put one person in the VIP line. Oh no. It created a situation where the VIP line would never, ever end, and that completely trapped the bouncer's attention.
This quote from the source material just nails it. Timothy's recursive promise is like a VIP who gets into the club and immediately texts their friend, hey, get in the VIP line. That friend gets in and then texts their friend. The bouncer, he's just following the rules. He has to keep letting these new VIPs in because the line is never empty.
And this visualizes that trap perfectly. The first promise Microtask runs, and the very last thing it does is queue up the next promise, Microtask. The event loop checks again, sees the new VIP in line, and lets them in. This cycle just repeats and repeats and repeats. Meanwhile, our set timeout and the UI rendering task, they're just stuck outside in the cold, never ever getting a turn. The rendering engine is literally being starved. So here's the crucial point. The fix isn't about getting rid of async code, not at all. It's about being smarter, being more intentional about which queue you're putting your tasks into. We have to, sometimes, purposely give control back to the browser. And here is the solution in action. On the left, you see the problem, that never-ending promise chain of VIPs. And on the right, the fix. Instead of queuing the next piece of work as another promise, Timothy rewrites it to use set timeout. See what he's doing? He's intentionally putting the next chunk of work into the general admission line. This gives the bouncer a chance to let the rendering engine in before he goes back to processing the next data chunk. And hey,
Here's a little pro tip for you. While setTimeout.0 works beautifully for this, if you're trying to sync up heavy work with actual animations, Request Animation Frame is often an even better tool for the job. You can think of it as a special kind of macro task that has a reserved spot right at the front of the general admission line, timed perfectly to run just before the browser repaints the screen.
All right, so after all of that, what's the new mental model we should be walking away with here? How do we avoid Timothy's trap in our own code and start building smoother, way more responsive applications?
Well, it really just comes down to these 5 rules. 1. Promises are VIPs. They create microtasks. 2. Set timeout and your UI rendering, they're in general admission. They are macro tasks. 3. And this is the big one. The VIP line must be empty before any macro task gets to run. 4. A long, unbroken chain of these microtasks will freeze your UI. And finally, number 5, to fix it, you have to break that chain by intentionally using a macro task, like set timeout, to give the browser a chance to breathe.
You see, understanding the microtask queue isn't just some neat trivia. It is a fundamental insight into how the web platform actually works. It pulls back the curtain on these hidden rules that are governing how our code runs. And that leaves us with a final, really important question to think about. What other invisible rules are out there, quietly shaping the behavior of the apps we build every single day?